We are at the last couple sections of chapter 6. We're going to look at 6.4 now, and then that will be followed by 6.5, and then that will complete chapter 6. Chapter 6 was about normal probability distributions. And in the first 3 sections, we looked at the standard normal definition, real applications of the normal distribution. And so that involved the idea that when you have a normal distribution of a population, and you know the mean and standard deviation, then you can label any value from the population's data set. You can label any value with a z-score that measures how far away it is from the mean of the data set. And that gives you an idea of how extreme that value is within the data set. Is it in the top 10%? Is it in the bottom 2%? By using the z-score and looking that up using table A2 or by using technology, you can see what portion, what percentage of the data is higher than that value in the data set and what portion of the data is below that value. Or wanting to know what value is needed to be in the top 10%, for example, you can also do that using technology or using the table backwards. And so that was the focus on the real applications of normal distributions in 6.2. Then in 6.3, we looked at sampling distributions and estimators. And that was a heady section. That was a bigger, more challenging section that we just did last time. So sampling distributions is not looking at how the data values themselves are distributed normally, but looking at taking samples from the population and then looking at a statistic from the sample, like the mean of the sample. And imagine doing that for different samples and then using the distribution of those samples' means. And that produces the sampling distributions. And that talks about how the sampling distributions can be used as estimators for the parameter values, for the values for the whole population. So there wasn't a lot of calculating being done in 6.3, but 6.3's ideas lead us to what we're going to talk about today, the central limit theorem. So in 6.4, the central limit theorem will be a theorem that allows us to then say, what can we do with the sampling distributions that we were discussing in 6.3? And how does that allow us to do problems? So we're going to go back to doing more calculations. So let's see what our key concept is here. In this section, we introduce and apply the central limit theorem. The central limit theorem allows us to use a normal distribution for some very meaningful and important applications. So what does it say? The central limit theorem says that for all samples of the same size n, with n greater than 30, the sampling distribution of the means of each sample, that's x bar, can be approximated by a normal distribution where the mean of the normal distribution of the samples is mu. And remember, mu stands for the mean of the population. And the standard deviation is the sigma value of the population divided by the square root of the sample size. So this is the mean of the population. This is the standard deviation of the population. So what the central limit theorem is doing is it's connecting or relating the mean and the standard deviation of the distribution of sample means to the mean and the standard deviation of the population values themselves. So remember from our previous sort of descriptions, what the central limit theorem is saying here is normal is the distribution of the samples. So imagine a whole bunch of X bars are collected. And this is sort of like a diagram that we saw that I'm reproducing here in 6.3. So every one of these little X bars that I'm drawing is a mean of a different sample. And if you look at the means of all the different samples and you form a distribution with those, this theorem says it can be approximated by a normal distribution. And that the mean of the sample means is the population mean. So this seemingly nonsensical sentence where the word mean is used 3 times is at the heart of the central limit theorem. The mean of the sample means, which are all these little X bars, and then you imagine you average out all those little X bars, you take their mean, and what you get is the population's mean. The mean of the sample means is the population mean. So that means that you can use sample means as an estimator for the mean of the population. But in addition to that, there will be some standard deviation. Standard deviation tells us how extreme a value is. So in this case, the standard deviation for the sampling distribution would tell us how extreme a particular sample mean is, how far away it is from the population mean. And this is very important since we are using often the sample's mean to try to infer something about the population's mean. Then we need to know how far away it might be from the population mean. But the standard deviation of the population, individual values, is not the same as the standard deviation for samples from the population. And so this formula tells us how the two are related. What it says is that the distribution from means of samples, the sampling distribution for X bar, has a standard deviation which is the same as the population standard deviation if you just divide by the square root of the sample size. And so the thing to take away from this right away, and then we'll illustrate this with examples, is that the larger the sample size, the closer X bar values get to the population's mean. What happens when I take a sigma value and divide by square root of n when n is bigger than 30? So let's use a simple example. Say n is equal to 36. That's bigger than 30. That means that we can use this normal distribution for the sampling distribution. It would be normal. And that would mean that whatever sigma was for the population, to get the standard deviation for the sampling distribution, I would be dividing by the square root of 36. The square root of 36 is 6. So that would mean that the standard deviation for the sampling distribution is 6 times smaller than the standard deviation of the population. That means when you take a group of 36 from the population and you look at the mean of that group, it's 6 more times likely to be closer to the population mean than when you take an individual's value from the population. We already think that the bulk of a population's values are closer to the mean if you have a normal distribution. But for a group size of 36 samples, then all of a sudden those mean value samples are 6 times closer to the population, making them a very good predictor. And the larger the sample size you use, the closer the sample means will be to the population mean. And we're going to see this illustrated graphically with some examples coming up. But that's the big idea here. Questions, comments, discussions about this? So think of it this way. If I'm imagining how far a person's value would deviate from the population's mean, so let's say a person's height. And let's say the mean value of heights is 5'7", and the standard deviation is 3 inches. Well, that means that 95% of everybody would have their height be within 2 standard deviations of the mean. So if the standard deviation is 3 inches and the mean is 5'7", that means that 95% of the people would be between 5'1" and 6'1", because the size of the standard deviation tells you how big a range is needed to capture most of the values. And the range rule of thumb, 2 standard deviations above or below the mean traps about 95% of the data. Well, now instead of just looking at an individual and saying how close are they likely to be to 5'7", and 95% of people are between 5'1" and 6'1", something like that. Well, then what if instead I took a sample of 100 people and I looked at the mean height of those 100 people? Well, the mean height of 100 people is much more likely to be close to the 5'7" average height of the population than an individual's would be. And if I'm doing 100 people, I would take the sample size of 3 inches and divide by the square root of 100, which is 10. And all of a sudden, instead of 3 inches in either direction from the mean for the standard deviation, I'm 3/10 of an inch. That means that if I take a sample of 100 people, 95% of all the possible ways I can take a sample of 100 people, 95% of the mean results of those samples, the mean heights of the 100 people, will be within 6/10 of an inch from 5'7". So instead of 95% of people being between 5'1" and 6'1", I will have 95% of my sample means be between 6.4 inches or 6.5 to 7.5. 95% will be within that 1.2 inch range instead of within that 1 foot range. So the larger the sample size, the tighter the mean values of samples will be close to the mean value of the population. All right, so let's try to illustrate this through further discussion and examples. Central limit theorem and the sampling distribution of X bar. Given that the population with any distribution, normal or not, has a mean of mu and a standard deviation sigma, we use those symbols, simple random samples of all size n are selected from the population. So these are the two givens, that you just have a mean of mu and a standard deviation of sigma from your entire population. With maybe it's a uniform distribution, maybe it's a skewed distribution. We're not even saying what the population distribution is. We don't know. And you always take simple random samples of size n. With those things given, then the central limit theorem allows us to say the following. Practical rules for real applications with the sample mean bar x, or X bar. So here's the requirements. To use the central limit theorem, you need to meet one of these two requirements. The population actually has a normal distribution itself. So we didn't give, that wasn't one of our givens, only that you have mu and sigma and size n. But if you then add that the original population has a normal distribution for the statistic, I'm sorry, for the parameter, or that the sampling size that you're taking is greater than 30. If either one of those conditions or both are met, then the mean of all the values of X bar, the mean of the sample means, is equal to mu. So that's what I said. The mean of the sample means is the population mean. Central limit theorem says that, as long as you meet one of those two conditions. The standard deviation, written as sigma with a little X bar below it, is the sigma of the population divided by the square root of n. And then using that specified sigma X bar, you could also calculate a z-score for a particular sample mean using the same formula you would, except instead of dividing by sigma for the population, you're dividing by sigma sub X bar, the standard deviation from the sampling distribution. So this is basically the notation with a couple of conditions, that one of which need to be met, to illustrate what I was just discussing in my weird little picture up here in my description. So everything I was trying to describe here, they are summarizing as well as showing you the notation used to describe the central limit theorem. Okay. All right, so the distribution of X bar cannot be approximated well by a normal distribution, and the methods of this section do not apply if the original population is not known to be normally distributed and you'd have a sample size that's too small, less than or equal to 30. So focusing on this just for a second. So you will see in our project that we have near the end of the semester that we'll probably start working on after midterm 2, that in the project, when you are collecting data from samples, the requirement from the data from the samples is that you have a minimum of 31 data values for each sample. And that's specifically for the central limit theorem. Because as long as you have more than 30 of your sample size, then you can apply the central limit theorem. Or if you happen to know the population is normally distributed, but typically the larger the sample size, the better anyway. And so for our projects, we're going to require a minimum of 31 samples size for each sample. All right, so let's consider these requirements, these considerations for practical problem solving, and we have 3 slides to think about this. So if you are looking at a problem or thinking about a situation, and we're going to want to use the central limit theorem where possible, you have to check requirements to make sure that it applies. When working with the mean from a sample, verify that the normal distribution can be used by confirming that the original population has a normal distribution or the sample size is greater than 30. The individual value of the mean from a sample. Determine whether you are using a normal distribution with a single value x or the mean x bar from a sample of n values. And we'll see this done in problems, so that's what will really illustrate this. The individual value is when you're working with an individual, then you would use the tactics that we used before, and you would get a z-score the normal way that we have before, or using StatCrunch. So again, if I take an individual student at DVC, and I come thinking about how extreme their height is, whether it's sort of near the mean value or whether it's in the top 10%, well, I would do that by getting a z-score for that individual's value of height based on the mean population's, the mean of the population height and the standard deviation of the population height. But if instead I'm working with the value of the mean of a sample of size n, then if I'm working with a sample of size n, if I know the population's heights are normally distributed, or if my sample size is over 30, then I would use the modified formulas they just showed. And of course, the mean value is still the same. It's the standard deviation that needs to be modified. And I would just do that by dividing by the square root of the sample size. I think we need to see these in action. So the standard error of the mean is what this sigma sub x bar is typically referred to. And it's sometimes denoted as SEM, the standard error of the mean. All right, so now we have a nice sample to explore this and see what it looks like in action. It's 7 slides long. The elevator in a car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds or 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. So what that means, what they're saying there is, if you load up all 27 people, that is the maximum for number of people, basically in terms of how many will fit in there for floor space or oxygen or whatever. Well, since the weight is 4,000 pounds, if I divide 4,000 by 27, that would mean that that group of 27 passengers would, on average, on the mean, would need to be 148 pounds. Otherwise, or less, otherwise they will exceed the 4,000 pound limit when there's 27 of them. So it says, we'll assume a worst case scenario in which the elevator is filled with all 27 possible adult, and they're all males, just they're saying that's worst case because males on average weigh more than females. Assume that adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Find the probability, this is part A, find the probability that one randomly selected adult male has a weight greater than 148 pounds. Find the probability that a sample of 27 randomly selected adult males, like one elevator's worth, has a mean weight of greater than 148 pounds. So are there any questions about the statement of the problem? What we're supposed to do, the ideas behind any of this before we look at description of the solution? All right, so they tell us that we can assume that adult males have weights that are normally distributed with a mean of 189 and a standard deviation. So this is mu, they're telling us, and this is sigma, they're telling us. So in part A, we're supposed to find the probability that if you just pick one adult male from the population, what is the likelihood their weight will be greater than 148? So this does not use the central limit theorem when we're using just for an individual. We would use the tactics we did before. We would grab the normal calculator off of StatCrunch and plug in the mean and standard deviation and say, what is the probability of being greater than or equal to 148? And it'll just tell us. Or if you were using the table of values, you would get the z-score with that mean and standard deviation of 148, and then look up that z-score on table A2 to see what population is greater than 148. So part A is stuff that we did before chapter 6, we did in chapter 5. Part B is where they then do what we're doing in chapter 6 in order to illustrate the difference between what we did before and what we can now do in with the central limit theorem. So in the central, and for part B, let's focus on that for a second. First of all, because we are trying to find out a probability of 27 people having a mean value of weight greater than 148, we're now looking at a sample mean, not just a sample person. And when we're looking at a sample mean, a mean of a sample, and talking about how that's distributed and how likely that is, that's when you want to apply the central limit theorem. And so given a group size of 27, that is less than 30. So the size of the sample itself does not allow us to apply the central limit theorem. However, it does say that we're assuming adult males have weights that are normally distributed. So that part up there, and I'll underline it here, assume the weights that adult males have weights that are normally distributed. With that assumption, then the population itself is normally distributed, and that's one of the conditions that will suffice to meet to use the central limit theorem. You need to either have a population that itself is normally distributed or have a sample size over 30. We do not have a sample size over 30, but we do have a population that is assumed to be normally distributed, so therefore we can apply the central limit theorem. The central limit theorem would then say, all right, we can get the standard deviation of the distribution of samples by taking the standard deviation of the population, which was given to be 39, and dividing by the square root of the sample size, which was 27. And then using that new standard deviation for means of samples of 27, I would then do exactly what I did in part A for the individual, but just with the adjusted standard deviation. I would go into StatCrunch, put in a mean of 189, but for my standard deviation, instead of 39, I would put in 39 divided by the square root of 27, whatever that comes out to be, like 10 or something. And with that new standard deviation, I would then say, what's the probability of being greater than 148? And since that standard deviation is smaller, that means that much more of the population will be closer to 189 pounds when you're doing averages of groups of 27. And therefore, a much larger part of the distribution of sample means will be greater than 148 than just the population of individuals. So that's my description of the ideas and what we would think about to do this problem. They're going to illustrate all of this for us in the next 6 slides. But again, the best thing up front is to think about what kind of a problem we have, what's the goal of the problem, how do I apply what I've been learning to deal with the problem, and eventually get the right answer. And so having discussed that up front, now they will illustrate it for us. Are there any questions before I proceed to their demonstration for how they did the problem? Now, I discussed using StatCrunch because that's been our technology of choice that I've been demonstrating, but they typically will say that technology can be used, but will often refer to the tables in the slides because they don't know which technology you might be using. So proceeding. Part A, use the methods. Remember, part A has nothing to do with the central limit theorem. And so it says use the methods presented in previous section because we're dealing with an individual in part A. The individual value from a normally distributed population, we would get the z-score. So they show the little formula for getting the z-score for 148 pounds using the mean and the standard deviation of the population. They got negative 1.05. And then they would, from that, get the population of being greater than that value. They're showing a nice little picture there. There is the distribution of the population's weights, male population weights, with mu and sigma given. And then they marking off on the graph 148, which is to the left of the mean. It's lower than the mean, but they want to know what portion of the population is greater than that. So that's been shaded. So the graph there indicates the answer to our question of the probability or the likelihood of getting somebody of that weight greater than 148 is equivalent to the portion of the area that's shaded there under the graph. So then they say they're looking that up on a table, and we would do all that on StatCrunch ideally. And they get 85%, 0.8531. And StatCrunch would give us the same thing. So then for part B, now it says we can use the normal distribution if the original population is normally distributed or n is greater than 30. The sample size is not greater than 30, but the original population of weights as stated by the problem has a normal distribution. That's our assumption. So because we meet that condition, sample sizes of any size will still yield a normal distribution. Because we are now dealing with a distribution of sample means instead of individuals, we must use the parameters mu sub x bar and sigma sub x bar. Mu sub x bar is just mu, it's still 189, but as I was saying, sigma sub x bar, you take the 39 that you had and divide by the square root of 27. Oh, it looks like that's a little less than 10, 7.5. And as I was saying, when the group gets bigger, the standard deviation of their distributions gets smaller. And so now we have a much smaller standard deviation than we would for an individual of the population. But then using that, they give us an adjusted graph. And notice how all the data has now squeezed in closer to the mean value. Much more of the data stays within a short distance from the mean value because the standard deviation for means is smaller than the standard deviation of the population in general. So that graph is a nice illustration of that. Then they can get their z-score using the adjusted standard deviation for the sampling distribution. And instead of getting a z-score of a little bit more than -1, all of a sudden the z-score increased for 148 in size to -5, almost -5.5. And you may recall, if you're getting familiar with z-scores, that z-scores bigger than 2 or -2 in size are large. The 95% of the data is within 2 standard deviations of the mean. So to go out more than, or like 5.5 standard deviations from the mean, that's a super extreme value. Very, very extreme value. It's much easier to find an individual who weighs less than 148 pounds than it is to get a group of 27 with an average weight of less than 148 pounds. Because even if there's a few individuals with that low weight, when you take 27 of them, it's probably going to balance out with some heavier folks, and it's much harder to get the mean of the entire group to be that low. So from the table, looking up this extreme z-score, they found that 0.9999, less than 1 out of 10,000, will be less than 148 pounds, and that almost all groups of a size 27 will have a mean weight greater than 148 pounds. And again, we could just get that value in StatCrunch by using the mean 189 and using the adjusted standard deviation of 7.51, and then looking up the score of 148. Final slide, 7 out of 7. So it says there's basically an 85% probability that an individual male will weigh more than 148 pounds. But there's, and then more accuracy is given. As you can see, the 9s just keep going. There's a 99.999998 probability that 27 randomly selected males will have a mean of the group weight of more than 148 pounds. Given that the safe capacity of the elevator is 4,000 pounds, it's almost certain that it will be overweight if it's filled with 27 randomly selected adult males. So there's about 7 slides left, and they do an introduction. So I'm going to look at this introduction, and then they just sort of do another example. And instead of doing their example on the slides, I'm going to try instead to go and do a homework problem for you so you can see this in action using StatCrunch. But let's look at this introduction to hypothesis testing. They introduced this idea a little bit before. We're going to be using hypothesis testing beginning in chapter 8 and then in chapters 8, 9, and after that. Identifying, but this is the key idea here, identifying significant results with probabilities. The rare event rule for inferential statistics. If under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or greater than we typically expect with that assumption, we conclude that the assumption is probably not correct. All right, so what the hell does that mean? So let's say I'm making an assumption like Well, I'm assuming that that the average height of students at DVC is 6 feet. Or let's say it this way, that the average height of students at DVC is low enough with a standard deviation small enough that if I make a door 6 feet, that it's going to be very rare for students to bonk their head there. Well, let's say I observe the doorway that's 6 feet, and I observe 100 people go through the door, and let's say half of them bonk their head there. Meaning that the mean height of that 100 group was about 6 feet, because half of them bumped their head and half of them didn't. Well, from that sample, it would suggest that either one of two things. The reason that happened is I just randomly happened to get 100 people that were taller than most students at DVC, that was an unlucky occurrence. But that maybe I'm still right, and that the average is low enough where most of the time that's not going to happen. Or the other possibility is that my assumption in the first place was wrong. Maybe my assumption that 6 feet was plenty good to let most people through was wrong. And maybe that sample that I got was just not a random occurrence that just happened to be some extra tall people, but that actually my problem is that there's a lot of people at DVC that are going to hit the head on that door. Well, how do I decide between which of those two is correct? Did I just get an unlucky sample, or is it that my assumption in the first place was wrong? So what this idea of hypothesis testing is saying is that if you have a hypothesis, which is this assumption, that's high enough so that most of the students at DVC won't have a problem. And then you have an example, a sample of 100. Then based on your assumption, you can ask yourself, well, if my assumption is correct, how rare would that sample be? So if half of the people going through bonking their head, if my assumption is correct, would only happen 1% of the time, if that's a 1 out of 100 or 1 out of 1,000 likelihood, well, that's such an extreme rare occurrence that it might be better for me to consider, well, I didn't just happen to get the 1 out of 1,000 group of students that are just happen to be tall enough to bonk their head half the time, that actually maybe my assumption was wrong in the first place. Maybe the fact that the first 100 people that I looked at bonked their head half the time, I guess I was wrong. I guess 6 feet is not high enough, because it's so unlikely that if I was right, that I would happen to get a group of so many people bonking their heads in this sample. This is the concept to hypothesis testing, that the way you can test an assumption that you have is to look at a sample. And if your sample deviates from what your assumption would predict to the point where your assumption would make what you saw, observed happen very, very rare, well, then maybe that's actually not as rare as it looks like, because maybe your assumption was just wrong in the first place. I'm definitely going to recommend you look at this slide, or where they talk like this in the book and they give this introduction, because this is a lot of times one of the bigger logical challenges for students in chapters 8, 9, 10, 11, is that they really are having a hard time understanding hypothesis testing. And so think about it in these early stages about what it's trying to say, and then we'll be more rigorous about it later. All right, so here's where I'm going to stop the slideshow introduction. Any questions about anything in the slides before we hop over to the homework and take a look at an example problem? Any questions at all? All right, there's about 10 or 11 minutes left, so let's make the move. So heading over to the homework, and I think I perused chapter 6, and it seemed like a good example of the central limit theorem. All right, so we are on homework number 8, sections 6.4 through 6.5 are covered, and this is early in the set, number 6 out of 29. Not a big homework assignment, only 29 problems on the 2 sections. But this is early in the assignment, and we can see that it is from 6.4, which we just introduced. So let's go similar question here, get a fresh look. So this will probably be somewhat similar to the elevator problem that they did as their example. This says, assume that females have pulse rates that are normally distributed with a mean of 75 beats per minute and a standard deviation of 12.5 beats per minute, and then complete parts A through C below. And then in part A, they say, if one adult female is randomly selected, find the probability that her pulse rate is between 71 beats per minute and 79 beats per minute. So this is kind of like a chapter 5 problem. So can anyone chime in with how I would do part A here?
We use the normal calculator from StatCrunch and put in the mean and the standard deviation and go into between to put in the between values that it should be.
Going to stat, calculators, normal. There's the normal calculator he was referring to. And he says go to between. So I'm putting in between. So that's exactly right. Thank you. Right on point. And the mean value they gave was 75. And the standard deviation is 12.5. And we're supposed to find the probability that a person chosen would be between 71 and 79. So I would enter those Z's, not 179. Try to enter this, watch my typing. And then I would say compute. And it gives us a nice picture, shows us on the graph. So this is the distribution of the population with the mean of 75 being right in the middle and the deviation, standard deviation of 12.5, showing how widely the curve is spread out over the data. And then we can use the area between these values on a normal curve to 4 decimals. And then I can check my answer, which I'll check in a second. So that's not using what we've been discussing in chapter 6. And so why is this different than a chapter 6 problem? Can somebody see that?
I thought we were doing
What's
this
that?
in chapter. I thought we were doing this in chapter 6. Wasn't that chapter 6, section 1? Or am I completely wrong?
I think we did this even back in, oh, well, you're right. I guess in practical applications, you're right. In 6.2, they did more problems like this. But so I shouldn't say chapter 6, but why is this not a 6.4 skill yet? Why is this not a central limit theorem problem yet?
We're talking about an individual.
Exactly. So in their discussions in the slides, when they were saying, look at whether you're looking at an individual or whether you're looking at a group of individuals, that's the distinction between, say, 6.4 and 6.2. Exactly right. Okay, so we check our answer. Yay. Then in part B, then it says, if 25 adult females are randomly selected, find the probability that they have pulse rates with a mean in the same range between 71 and 79. So in part A, it was for an individual. Now it's for a group, a sample of 25 people that are randomly selected. And so we want to do the same thing we just did, but because now we're using a group here, we use the central limit theorem, and it tells us that we can do the same thing with a modification. So how would I modify what I did here for part B?
We need to calculate a new standard deviation using the new sample amount.
Exactly. So the mean stays the same. The range stays the same, but the little 12.5 standard deviation for the population needs to be replaced with the standard deviation for sample means. And the way we do that is by taking the original population standard deviation and dividing it by the square root of the sample size. And so they were nice. They gave us a sample that was a nice perfect square, 25. So if I take the square root, I get 5. So I would take this value and divide by 5. 12.5 divided by 5 is going to be 2.5. Or you could do it on a calculator if it doesn't come out nice. And then I just do the same thing. So to 4 decimals, go to there. Questions about how we applied the central limit theorem to part B, or why we applied the central limit theorem to part B? So there's a part C where they're probably going to make us try to think or something. Why can the normal distribution be used in part B? Meaning we use the normal calculator. We're using a normal distribution in our part B calculation. So it's saying, why can we use that for part B, even though the sample size does not exceed 30? There's only 25, and it does not exceed 30. So why is it still okay to do what we did?
It says in the question that the pulse rates are normally distributed.
Exactly. So you want to be keyed into this because if you have small sample sizes, then you need to look for the requirement of being understood that the population values are normally distributed. But once you get a sample size over 30, you don't have to worry about that. And that's why sample sizes over 30 are a great starting point for any statistical work. All right, now I've got to pick one of these. Since the distribution of individuals, no, it's not, it's of a group. Since the mean pulse rates exceed 30, no, they don't. Since the distribution is of a sample means, not individuals, the distribution is a normal, no, that's not why. Since the original population was normal, then the means is normal. That's part. So I read them from last to first. Turns out the first one was the right answer.